Hi everybody, welcome back to another episode of MSI Recap, and today I'll be going over the final class of uh, my first year actually. So I'll be talking about MSE 160, Molecules and Materials. Uh, yeah, if you don't know already, my name is Jason. I just finished my second year of engineering science at Uoft, and yeah, let's get right into it. So MSE 160 is a year one winter course I took, and when I took it, the instructors were Professor Nogami and Professor Ramsay. So MSE 160 was an interesting course. It was sort of a material science course. It was less focused on like chemistry, so I guess like the name is maybe a little misleading. It's not super focused on chemistry, but there are definitely concepts that are borrowed from there. So we talk about uh, elasticity, elastic behavior of materials. We talk about crystallographic planes and directions, crystal structures, imperfections and strengthening mechanisms, polymers, atomic models, metals, insulators, semiconductors. There's even some thermodynamics, as well as phase equilibrium and phase diagrams. And yeah, today I'll be going over a problem from problem set 3, which is the final problem set of the course. I'll be going over question 9, and I submitted this on April 16th, 2021. So the topics of this question include phase diagrams, tie lines, and the lever rule. So this is the diagram that was provided with the question. Um, it says the following two questions pertain to this phase diagram for SNPB. So that would be uh, tin and lead, and this is a phase diagram. So what it's showing is it's showing the different phases that you can achieve in a solution of tin and lead depending on the composition. So on the x-axis, you see the composition with respect to the weight percentage of tin, and the y-axis is simply the temperature. So you have all these different phases. So for example, alpha, alpha plus beta, alpha plus L, or plus liquid, liquid, beta plus liquid, and beta. So these are the questions that it's actually asking. So for an alloy containing 20 weight percent tin at 110 degrees Celsius, answer the following. So what are the phases present? What is the composition of each phase? And what amount in weight percent of each phase is present? And then for an alloy containing 80 weight percent tin at 200 degrees Celsius, answer the following, the same questions pretty much. So essentially, we can start off with the phase diagram and go from there. So we'll start off with the first case. So 20 weight percent tin at 110 degrees Celsius. I've indicated that with this black X here. This is all sort of very approximate stuff. We're just using the diagram as a visual aid and to perform some rough calculations. Um, a lot of it deals with like eyeballing the values and just giving a rough estimate. It's not going to be extremely precise. So as you can see from that diagram, we were in the region where the phases present were alpha and beta. And we should note that alpha would be a solid solution of tin in lead, and beta would be a solid solution of lead in tin. And this is just based on the fact that beta is going to be present when there is, uh, beta is going to be present alone when there is a high amount of tin, and alpha is going to be present alone when there is a very low amount of tin and a high amount of lead. So now we can draw a tie line to determine the composition. And so what we see is when we draw this horizontal line, we intersect um, the line the boundary between alpha and alpha plus beta, we intersect it at a 6 weight percent tin. We intersect this boundary between alpha and beta at around 98 weight percent tin. So what we can see is that the composition of alpha is going to be 6%, so that would be 94 weight percent lead, and the composition for beta would be around 98% or 2 weight percent lead. So now we can use the lever rule, and basically we can determine the composition of the solution we actually have. So we can calculate that it would be 85% alpha and then 15% beta, just using this lever rule we have here. Now moving on, we can consider this next question, which would involve 80 weight percent tin at 200 degrees Celsius. So again, I've indicated that with this black X, and you can see the region we're in. The phases that are present are beta and L. L means liquid. And again, beta is a solid solution of lead in tin. If we draw the tie line, we can see that we have around 73% weight percent tin in the liquid phase, and then 98% tin in the beta phase. Again, that's just summarized here. And I again use the lever rule to find that we have 28% beta and 72% of the liquid phase. Again, this 1 minus just comes from the fact that the total percentage must add up to 100%, given that we only have 2 phases. But yeah, hopefully that was a relatively simple question to go over. And before I end up this video, I'd like to make some quick acknowledgements. So I'd like to thank Professors Nogami and Professors Nogami and Ramsay for the course and the term test content. I also like to thank my tutorial TA, Desmond. I believe actually he was responsible for writing these problem sets. So I'd like to thank you for that. As well, I'd like to acknowledge the individuals whom I took this template from for my presentation. But yeah, I hope you enjoyed this video, and when I make more videos, hopefully I will be covering some second year courses, which will be very exciting. So I hope to see you then. Take care.